Usually when scientists talk about exobiology, they discuss the types of planets on which life can arise, the types of biology that can arise, and so on. But rarely do they ever mathematically quantify anything of the sort. One of the few exceptions is the Drake equation, which tries to give a numerical answer to how many civilizations there are in the galaxy. Today, I set out to prove why the Drake equation is wrong. If you are unfamiliar with the Drake equation, please watch one of the many videos on YouTube about the topic. This mess right here is the traditional form of the equation. Going from left to right, n is the number of actively communicating civilizations in the galaxy, which is computed as a factor of all of the other terms. These terms are a combination of rates, averages, and probabilities. The first of these is R star, that is, the number of stars which are born in our galaxy each year. This is multiplied by f sub p, the fraction of stars which have planetary systems. N sub e is an average of the number of potentially habitable planets in a planetary system. Logically following from that is f sub l, or the chance of life developing on a habitable planet. After this, we come to the factor concerning evolution. That is f sub I, the likelihood that life on a planet will become intelligent, followed by an intelligent life form's chance of being able to communicate with us, f sub c. The very last factor in the equation is L, the average time in years that a civilization can communicate. It sounds confusing for sure, but in fact, it is quite simple to explain if we multiply one factor at a time. First, we take the product of r star and f sub p. Imagine r star is 10 and f sub p is 0.8. If there are 10 new stars per year, and 80% of them have planets, then 8 new planetary systems are formed each year. So, r star times f sub p is the rate at which planetary systems form. Multiplying that by n sub e, we get the rate at which habitable planets arise. Evidently, the product of anything up to L is a rate. The total product of everything but L is the rate at which communicating civilizations arise, which will be called r sub c. The last factor is a bit harder to understand, but the best way to explain it is once again to give the factor's demonstration values. So, let's assign r sub c the value of 0.5. This would mean that one new civilization arises on average every other year. If we also say L is 300, then, on average, all of the communicating civilizations alive would be born within the last 300 years. And since there are 150 civilizations born in the last 300 years, that is 150 civilizations alive today. There are issues with the equation, however. One problem is the lack of a factor relating to the so-called galactic habitable zone, the area of a galaxy in which life can arise. Too many stars, and radiation is lethal to any sort of biology you can think up because of its general property of disturbing the bonds in molecules. While this may technically be part of n sub e, this is best to think of as a separate entity. We will call this new factor f sub g, the fraction of planetary systems which are in a suitable position in the galaxy for life to exist. Note that while current scientific evidence points towards the existence of a galactic habitable zone somewhere in the galaxy, if it is possible for complex life to exist anywhere in the galaxy, then it still works. Just assign f sub g the value of 1. Another thing which may occur to some is that it seems to assume that only one communicative species can ever evolve per planet, something which is obviously wrong. In fact, Earth itself may have multiple sapients already, depending on the definition. There is a chance, however small, that other intelligent species on Earth may become civilized as well, and who knows, ravens may be plotting to take over in case of our extinction. Okay, they're not plotting, but still. Taking that into account, we will replace f sub c with n sub c, the average number of communicative species which evolve on a planet bearing intelligent life. There's one last addition that must be made, again relating to civilizations. The Drake equation seems to be counting. Actually, what exactly is it counting? The total number of communicating species? The total number of communicating civilizations? Stars with communicating civilizations around them? These are subtly different, and it is quite important to define what we are counting for this variable, so we will count planets with communicative species, since each planet tends to function as its own civilization. In order to fulfill this definition, we will add yet another variable, n sub p, the average number of planets which a civilization inhabits. Okay, now we're done pulling it apart, right? Nope, not even close. R star is evidently a very vague factor, and it's hard to precisely define it. It is said to be the rate of star formation. But when? Not now, because stars forming now obviously don't harbor life. Maybe on average over the life of the Milky Way? Nope, not that either, since civilizations are probably born around stars close to half the age of the Milky Way. I've seen a lot of beating around the bush with this factor, and in order to make this actually work, it would need to be the rate of star formation at the average time a current civilization star is formed, and judging from how poorly you probably understood what I just said, this factor is too complicated and might need its own equation if we were to keep it. Instead, there is a much simpler solution to this, and that is to replace the factor with n star, the actual number of stars that exist right now. This means that all the factors up to L would be the total number of civilizations that have ever existed around living stars in the Milky Way. In order to keep this in the present, divide L by the average lifespan of a star and call the quotient F sub L. This is the probability that a civilization around that star exists right now, or the fraction of counted civilizations that still exist. Or is it? The issue is, of course, now that the probability of finding a civilization around a star is not evenly distributed. That is, you are probably more likely to find a civilization around a middle-aged star, something not accounted for, which means that we have created a new problem. This is very similar to the vague R-star problem, and again would need very precise measurements and potentially its own equation to solve it. And that's not the only problem with R-star or N-star. It may not be obvious, but it assumes something, and that's not something which you want. It may seem like something that you would never disagree with, but it is assuming that all intelligent civilizations need a star. And while this may be the case, there are so many rogue planets in the galaxy, some have calculated there may be more rogue planets than normal ones, that perhaps there are many such civilizations. With this rid of, there is no point to keeping F sub p either, since that also has to do with stars. So, n star gets replaced by capital N sub p, the number of planets or rogue planets in the galaxy, F sub e gets completely dropped, and N sub e gets replaced with F sub e, the fraction of planets which are habitable. Finally, in order to make the Drake equation truly present tense and avoid any of the equations within an equation, some of its factors will become present tense, as you will see in a second, and we will remove F sub L. We will also drop n sub c because this is in the present, and using the system of counting civilizations we established earlier, simultaneous intelligent species do not count twice. The final revised equation is as such. The number of civilizations in the galaxy equals the number of planets or rogue planets in the galaxy times the fraction of these planets in the galactic habitable zone times the fraction of those which are potentially habitable times the fraction of these planets which have life right now times the fraction of life-bearing planets which have intelligent life right now times the fraction of intelligent life that is communicating right now times the average number of bodies a civilization is inhabiting right now. I personally would not find this equation very useful at all, and yet, to make it tell the truth, this is what it all comes down to. Tense agreement. What your English teacher has been nitpicking on your essay is essential to having a better understanding of exobiology. Or rather, in this case, having a better understanding of what we actually don't know about exobiology. The Drake equation, when put in its valid form, requires much more measurement than speculation because of its lack of time independence. That time independence is what made the equation originally seem so useful and simple, but now showing that it cannot be correct without present tense makes the factors a whole lot more difficult to figure out. In fact, with the correct version of the equation, it may be impossible to derive correct values for the variables without already knowing how many civilizations there are in the galaxy. But that's an argument for another time. Bottom line, the Drake equation is wrong. Thanks for watching. If you enjoyed the video, don't forget to subscribe to Speculative Evolution to see more awesome videos about the topic. Please leave any questions you have in the comments. And if you want to converse with other speckers, go ahead and click the links in the description to Speculative Evolution Wiki and forums. See you in the next video! I know it! I know it for a fact! Ravens are gonna take over after we destroy ourselves, and they're doing everything to try to make us go extinct! The reason that they seem to be so absent-minded all the time is that they're plotting their mastermind plan to accidentally begin World War III and destroy the human race! They're gonna kill us all!